Next we're going to talk about alkenes. There's actually a couple lectures we're going to have on alkenes, and we'll start by looking at the structure of alkenes and the synthesis of alkenes. So an alkene is defined as a molecule containing a carbon-carbon double bond. And when we look at the structure of a carbon-carbon double bond, we remember that it is a planar structure. Each of these carbons has sp2 hybridization. And that requires a trigonal planar geometry. Connecting the two carbons are two bonds. We would describe these bonds as one sigma bond and a pi bond. The way a sigma bond is made is we join the hybrid orbitals on each carbon. So this is an sp2 overlapping with an sp2 hybrid orbital. And for the pi bond, the way we form a pi bond is we have a p orbital on each of these carbons, and that's overlapping to form the pi bond. This model has a very nice picture of what an alkene looks like. Here in the gray, we see the sigma bonds. They're all planar. And on each carbon, each sp2 hybridized carbon, we have a p orbital. Remember, that's the dumbbell-shaped type orbital. And it's overlap of the top half of that orbital and the bottom half of that orbital that comprises a pi bond. So a pi bond is a cloud of electrons above and below the plane of the molecule. So we could describe the pi bond as being the overlap of a p orbital and another p orbital. So if we want to do a 3D sketch of this molecule, one way to draw it is to draw all the sigma bonds in the plane. That's certainly an easy way to draw all the sigma bonds. Trigonal planar means these bond angles are about 120 degrees. But then our 3D sketch should also show the pi bond. And where the pi bond is, if the molecule is in the plane, then the pi bond is perpendicular to that plane, sticking straight out and straight back. So we can sketch that as maybe a wedge and a dashed lobe, a wedged lobe and a dashed lobe, one on each carbon. And then we can show some overlap at the front and back. Okay, so what we need to show is that the p orbitals are perpendicular to the sp2 plane, or orthogonal. And we need to show that they're perpendicular. So actually another way that we can draw this molecule is to draw it so that the p orbitals are in the plane, the pi bond is in the plane. So we could draw our p orbitals nicely shaped, and our pi bond, again, top and bottom, shows overlap. Okay, but when we do that, what happens to the hydrogens? If they're hydrogens here, or the sigma bonds, whatever they're attached to. The sigma bonds are now, these two are projecting out toward you, and the others are pointing back. So the rest of the molecule is now perpendicular to the plane, and so we need to show them as a dash and a wedge. So when we go to draw this, what we do is we tilt it just a little bit so you can see the wedged bonds and the dash bonds as well. You want to make sure you use the same angle, though. Either tilt it up a little or tilt it down a little. You don't want to try and twist the molecule and draw it like that. So here I drew both wedged bonds pointing down toward the bottom of the page. That would be an acceptable drawing. So either of these 3D sketches look really good as a way to draw an alkene, a carbon-carbon double bond. What else do we know about pi bonds? That we've seen a little picture of them. We should also know that pi bonds are higher in energy than sigma bonds. The p orbitals are higher energy that are coming together to form those pi bonds. So that's going to make them more reactive. We're going to see lots and lots of reactions that break pi bonds and all sorts of reactions of alkenes that we'll talk about in our next lecture. Okay, and also we want to note that pi bonds are electron rich. They're a good source of electrons. Those two electrons are fairly loosely held. They're fairly available. So what are some things we associate with electron-rich species? They could be a nucleophile. What does it mean to be a nucleophile? That means you can react with an electrophile, right? So we'll see a lot of reactions of alkenes with electrophiles. And it can also be a base. What does it mean to be a base? An acid is something that donates a proton. A base is something that accepts a proton. So in other words, it can be protonated. And many of our mechanisms for alkenes are going to start with reaction with an acid, and our very first step is protonation of that pi bond. We should also review some things that make alkenes stable. Well, some of the things we've already seen before, but some other things that we want to know. One feature is that an alkene is more stable if it has more alkyl groups attached to it, more carbon groups, the better. So if we take a look at this carbon-carbon double bond, it has a possibility of having four alkyl groups attached. In this case, we have 1, 2, 3 of those positions filled with alkyl groups, so we describe this as being tri-substituted. And we know that is that's going to be more stable than for this alkene. Our carbon-carbon double bond is here. How many alkyl groups do we have attached? We have just 1 and 2 carbon groups attached here. So this we could describe as di-substituted. And it is less stable. A di-substituted alkene is less stable than a tri-substituted alkene. Another way you could describe these two particular alkenes is you could say that this one is internal to the carbon chain, while this one is terminal. The second one is terminal. It's at the end of a carbon chain. That's also not a good place for a double bond to be. So we can look for features like that to determine whether or not our alkene is more or less stable. Okay, and we can also look for the relationship of the groups that are attached on a double bond. And for example, if we have a di-substituted double bond, we know that we could have a cis arrangement or a trans relationship. The cis one is when they're both facing on the same side of the double bond. Trans is what we call it when they're on opposite sides of the double bond. And the trans is more stable. And that's because by forcing these two alkyl groups in the same direction, they have some steric strain, some steric hindrance there, and so there's some more crowding. So cis is going to be less stable than trans. Okay, the exception is when we have a double bond within a ring. If we take a look at something like this, cyclopentene or cyclohexene, now in order for these two groups on the double bond to connect in a ring, they actually must be pointing in the same direction on the double bond. It has to be the cis conformation. So for small rings like these, it's cis only. It is possible to have trans if you get to a larger ring. So it's possible if it's 7, that's still pretty unstable, but as soon as you get to an 8-membered ring, you can have, so for example, cyclooctene can either be cis cyclooctene, where we draw our 8-membered ring and we put a double bond in there, and now we see that those two alkyl groups are cis to each other, or it could be trans cyclooctene. And when we draw this, it gets a little more complicated because the molecule ends up being twisted because we put one alkyl group on the opposite side of the other. But if the ring is large enough, then those two alkyl groups can still come around and be connected. So it's possible to have cis or trans. Let's see, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons there. And this is kind of passing behind the double bond, is kind of the 3D sketch. Try building these models and you can get a feel for what cis and trans looks like. Okay, but if it's a smaller ring, if we just have cyclopentene or cyclohexene, we do not put the word cis as part of that name because it's impossible to have trans there. So cis is assumed, and cis is going to be much more stable because it's a more stable ring that way. Okay, if we happen to have more than one pi bond, something we can look to for stabilizing the pi bond is conjugation. Okay, conjugation is when we have a pi bond and then a sigma bond and then another pi bond. So if our pi bonds are separated by just one single bond, that's going to be a good relationship because what happens, and this is an example where we have a double bond, single bond, double bond. So this is conjugated and this is not conjugated, because separating these two pi bonds, we have an sp3 hybridized carbon. And when you take a look at the p orbitals here, we know that this pi bond is a p orbital and a p orbital, and this pi bond is a p orbital and a p orbital. And so look what happens when they're conjugated. We have p orbital, p orbital, p orbital, p orbital. We end up getting delocalization of those pi electrons over all 4 of these atoms. And so what we get is resonance stabilization. And we'll be looking more at these conjugated systems down the road. But for now, we want to see it. If we ever see it, we want to recognize that as something as being stable, and that's more stable than having this pi bond totally isolated from this pi bond, and there's no relationship between the p orbitals from one to the other. So this is going to be more stable, and the non-conjugate is going to be less stable. So that's something else we can look to stabilize a double bond if we can. And finally, if we have something like this is an example of a bicyclic compound. It's a bridged compound. We have 2 rings in this molecule, and when you have a double bond in a bicyclic compound like this, we're going to look for the bridgehead carbons. The bridgehead carbons are defined as those that are shared between multiple rings, so where the 2 rings come together and there's a juncture. So this is a bridgehead carbon, this is a bridgehead carbon. So when you look at this molecule from the perspective of the bridgehead carbons, you see that these carbons are connected by 3 bridges. Here's a 1-carbon bridge, here's a 2-carbon bridge, here's another 2-carbon bridge. So we call these bridgehead carbons. And it turns out that having a double bond attached to one of those bridgehead carbons is very unstable. Okay, so this molecule is not going to want to exist. It's going to be highly unstable. And so it's okay to put a double bond somewhere else in the bicyclic compound. So it's okay to have a bicyclic compound. So over here it would be okay because the double bond avoids the bridgehead position. So this is known as Brett's rule, and you might come across some examples where you are looking for where to put a double bond as a result of a reaction, and we want to avoid bridgehead carbons. Okay, now this alkene stability can be measured. This is something that we can find some evidence for, the various rules that we're looking at, by doing a reaction called the hydrogenation reaction and measuring the heat of that hydrogenation. And we're going to be talking about that in our next lecture when we look at that's one of the many reactions we'll be studying that alkenes can undergo. So how would we make an alkene? If we want to put a carbon-carbon double bond into a structure, there's really 2 major approaches that we would want to take. One of them is going to be an E2 reaction on an alkyl halide. And let's see an example of that. How about if we wanted to transform this given starting material into the desired product, okay? And what a transform problem looks like is it means provide the necessary reagents to convert one to the other. More than one step might be possible, so it might not just be one reagent that you're putting in there. It might be multiple steps to convert one to the other. Okay, so if we compare our starting material to our product, we see that an elimination has taken place, right? It must be an elimination because we've formed a double bond. We've lost the bromine, the leaving group, but we've also lost a hydrogen. And so what we need to consider is what mechanism do we want to employ in doing this elimination? We have 2 choices. It could be either an E1 elimination or an E2 elimination, and there's some benefits to some, and some might be more suitable. Let's think about an E1 elimination. That was the mechanism. That was the multi-step elimination mechanism. It started by loss of a leaving group to form a carbocation. So carbocations are involved in the E1 mechanism. And would this be a good substrate to form a carbocation? We have our leaving group on a primary carbon, so that would give us a primary carbocation, and that is not a very good carbocation. That would be highly unstable. Okay, so I don't think an E1 is a good idea here because we have a primary leaving group. That would give a primary carbocation, and that would most certainly rearrange. And so I think we should avoid trying to do some kind of unimolecular elimination and count on a carbocation. So instead we're going to do an E2. E2 elimination is where we had some strong base attack in a single-step mechanism, attack the beta hydrogen, form the pi bond, kick off the leaving group. Right? So that's our E2. So what we need here is we need a strong base. We need a strong base. And if you had to think about a strong base, maybe sodium hydroxide comes to mind. That would definitely be a strong base. But let's take a look at this starting material, this N-bromobutane or 1-bromobutane, and think about its reaction with sodium hydroxide. Yes, it could do the E2, but is there another reaction that hydroxide can do? Remember that hydroxide is can be both a base and a nucleophile. So we have our competition here between SN2 and E2. And because we have a primary alkyl halide, what would be favored? There's no steric hindrance. S2 is going to be favored. So sodium hydroxide wouldn't work because that would give us the substitution product. How can we force the elimination then? How can we suppress the substitution, the backside attack of the SN2? If there's some way we can increase the sterics of that backside attack, then that would help us, that would force the E2 and be favored over the SN2. So how about if we just used a different base? What would be a bulkier base than sodium hydroxide? How about T-butoxide as a base? T-butoxide has a terp-butyl group. Now it's very bulky. This is bulky, and so E2 is major. Even with a primary halide, the terp-butoxide favors the elimination. Okay, so all we need to do in this case are reagents. Can be done just in a single step. Is we use T-butoxide. Maybe we can throw in some heat if you want. That usually favors the elimination as well. But all we need in this case is a strong, bulky base. So the E2 is a very good method for forming alkenes, very reliable, single step. Let's review some of the features of the E2. Remember the stereochemistry of the E2. There was a relationship between our leaving group and our beta hydrogen. They had to be anti to one another. We called it anti-elimination. Anti-elimination. So we need to be able to achieve that stereochemistry in order to do the E2. Our regiochemistry, this was governed by Zaitsev's rule. We wanted to get the most stable alkene. Now in this case, we didn't form a very stable alkene, did we? It's terminal, it's monosubstituted, but because there was only one beta hydrogen that was, one type of beta hydrogen that's possible, this is the only E2 elimination product that's possible, so this would be in fact our major product. Zaitsev's rule comes into play when we have more than one beta hydrogen from which to choose, and the one we select is based on the one that would lead to the most stable alkene product. Okay, and finally, how about the SN2 versus E2? Because we're going to have that competition with our strong bases. They can also be nucleophiles. So as usual, as we increase our sterics, we know that is bad news for the backside attack for the SN2. So that's going to increase the proportion of the E2 elimination product. So we need to, if we want to increase our sterics, we need to have a nice repertoire of bulky bases from which to choose. Okay, and of course the T-butoxide is the one we're most familiar with, the T-butoxide. But there's some other ones you can do as well. There's some nice amine bases. Amines have nitrogen in them, and they usually have some groups attached on that nitrogen. So for example, triethylamine, a nitrogen with 3 ethyl groups attached to it, kind of like the terp-butyl group, very big and bulky, so that's very good for doing eliminations. Or diisopropyl amine has a nitrogen with 2 isopropyl groups on it. Look at all that steric hindrance, all that bulk. So diisopropylamine is another example of a base that's good. If you put that in there with an alkyl halide and warm it up, then you can have a good bet that E2 is going to be your major product there. Now, a second approach besides doing the E2 elimination is to start with an alcohol and do a dehydration reaction. So here's an example of an alcohol, and in order to do a dehydration, we're going to react this either with H2SO4 and heat, or maybe H3PO4. These are the ones we'll probably see most often, so some strong concentrated acid and heat. And what happens is we get an elimination reaction to take place. So we form an alkene product. We start with an alcohol, and we form an alkene. And what did we just lose? What has been eliminated in this elimination reaction? We lost the OH, of course, but remember we also lost a beta hydrogen. So we lost an OH and an H. It means we have a loss of H2O. That's why we call this reaction the dehydration reaction. because just like when you're out in the desert or you're running and you're dehydrated, you're low on water, dehydration means you're losing water. So the other product in this reaction is water. So let's think about the mechanism for this. How can this alcohol get converted to an alkene? How can it lose water? Well, clearly we have very strongly acidic reaction conditions. So what do you think our first step should be? In a strong acid, we need to protonate something. So let's look at our alcohol and think about where to protonate. We really only have one choice, on the oxygen. And that, in fact, is going to be our first step of the reaction. Let's just use HA to represent our strong acid. 2 arrows to do a proton transfer, and we can protonate the alcohol OH group. Okay, great idea for a first step because we're in strongly acidic reaction conditions, so protonate. Okay, now what does that do for us though? Why would that be something that might move us toward a product? Well, remember, once we protonate an alcohol, we turn that OH into a very good leaving group. Very good leaving group. It's going to be, it would be water once it leaves, very stable molecule. And so we now have a leaving group to do our elimination. So now we should think, do you think it's going to be an E1 elimination mechanism, an E2 elimination mechanism? E2 means we have a strong base come in and attack the beta hydrogen to kick out this leaving group. Is that what happens? Do we have any strong bases in this reaction conditions? In these reaction conditions? No, of course not. We have very strong acid conditions. So it can't be an E2 elimination. It can't be an E2 because there's no strong base. So our only other choice is to be an E1. What does it mean to be an E1? It means our leaving group just leaves on its own. So in acidic conditions, that's what we get. Our leaving group leaves on its own. So this next step is loss of leaving group to give a carbocation intermediate. And this carbocation can go on to be a carbon-carbon double bond, to be an alkene. And this is how the E1 continues. How do we do that final step? Remember, we're losing water, we're losing the OH leaving group, but we're also losing a beta hydrogen. So what we do is we look to one of the hydrogens on the neighboring carbon. I'm going to choose over here because that's going to give me a double bond that's more highly substituted, that's more stable. You can see that's the major product that was shown here. Okay, and I could just use A minus as a good base that was formed in that first step. I can use A minus to come back in here and deprotonate. So carbocations can be deprotonated to form double bonds to form alkenes. So this last step we could describe as deprotonate, or the loss of the beta hydrogen. We know that has to be part of any elimination, so we want to put it in that context. So we're going to protonate, lose our leaving group, and deprotonate. That's our E1 mechanism for dehydration. So what are some other things that we want to know about this dehydration mechanism? Because it's the E1 mechanism, it's going to give the most stable alkene, so this will also follow Zaitsev's rule. It involves a carbocation. We know carbocations can rearrange, so if there's a possibility that we can have a hydride shift or an alkyl shift to go to a more stable position, a more substituted carbocation, that can happen, that will happen. And taking a look at our reaction conditions, remember that we're dealing with a very, very strong acid, and we need that to make OH a good leaving group. So we really have to have something like sulfuric acid as our catalyst in this reaction. Okay, so now in my mechanism, I just used HA to represent sulfuric acid. That's kind of a safe species to use in a mechanism to represent a strong acid. But let's just remind ourselves what H2SO4 looks like. Okay, this is H2SO4, and so after it protonates something, after it's used as an acid, we're left with A minus, and that's this species right here. Okay, now why is sulfuric acid such a great acid? Why is it such a strong acid and so willing to donate its proton? Well, we could take a look at its conjugate base. This is the conjugate base of sulfuric acid. Do you think this is a pretty stable molecule, or is this pretty reactive? What do you think about it? It's got an O-, and so sometimes we consider that to be a strong base, but this is not a strong base. And that's because this O- is resonance stabilized. Okay, we can draw several resonance forms for this. I'll just draw one here. Okay, but this negative charge can also be delocalized on the third oxygen, the other oxygen down here. So that negative charge is equally delocalized over all three of these oxygens, which means it's very, very stable and is resonance stabilized. So we have a very weak conjugate base. It's very stable, very unreactive, very weak. And we would expect that for something that is the conjugate of a strong acid. Okay? Because it is so stable, that makes it non-nucleophilic. Okay? In other words, there's going to be no SN1 competition. Normally, up till now, every time we've seen a carbocation, we've used that carbocation and had a nucleophile add to it, and we've done a substitution reaction. And the only time we've seen elimination, we said, well, that was just usually a side product for our substitution. Substitution is usually favored. Well, the dehydration reaction is the one example that deviates from that norm, and it's simply because in these reaction conditions, we have no nucleophile to add to the carbonyl, to the carbocation. All we have is a strong acid and its weak conjugate base, and so once you form the carbocation, your only choice is to dehydrate and to eliminate and form the alkene double bond. Okay? You can think of the A- like a spectator ion. You can use it as a mild base to deprotonate something that needs deprotonating, but it's not going to be something that's going to be nucleophilic, that's not going to be participating in the reaction. Okay, and what I wanted to do is I wanted to compare an acid, strong acid like H2SO4 with another strong acid like HCl. Okay, what we just said about H2SO4 and heat, this looks like what kind of reaction conditions? This looks like you're going to lose water. It's going to be dehydration, strong acid and heat on an alcohol. So what would that product look like? We have 4 carbons. We're going to lose water. And so we would form the double bond between the middle 2 carbons here. That's more stable than being at the end. We can keep this trans relationship. That would be more stable. So remember, we could also form the cis butene product, but that's going to be less stable. So that would not be our major product. Our most major product is the most stable alkene we can have after rearrangements if they're necessary. Okay, so in other words, we would expect E1 elimination to take place with H2SO4. Now, how does that differ when we react it with HCl? Well, HCl is unique because not only is it a strong acid and a source of proton, it is also a source of Cl-. Okay, so it's a strong acid plus it's a nucleophile. It's a source of a nucleophile. So what happens when we react an alcohol with a halo acid like HCl? We protonate to form a good leaving group, and then the halogen replaces that leaving group. We get a substitution mechanism taking place either by the SN1 mechanism or the SN2 mechanism. Both of those can happen with the halide. We can form a carbocation, or the halide can do a backside attack. Okay, but with an acid like HCl, we get substitution because if there is a nucleophile present, that nucleophile will want to attack the carbocation. With H2SO4 heat, there is no nucleophile present, so once we form the carbocation, our only choice is to eliminate and get the alkene product. Okay, and let's try another example here. Here we're given a reaction and we're asked to provide a mechanism. And it looks like we have these 2 methyl groups here. Remember, our line drawing means these are methyl groups. And it looks like those methyl groups used to be on the same carbon and now they're on different carbons. So I think we're going to have to do some kind of rearrangement in our mechanism to account for that. So how do you think we should get started? I see that strong acid, so I'm going to protonate as my first step. So I could use HA to protonate. Okay, every step in this mechanism, the dehydration mechanism, is reversible. So this oxygen now has just one lone pair. It has a positive charge. I've protonated. And after protonating, now I have a great leaving group that can leave. So I show this bond breaking and leaving with water. So this is where I just kicked out my water molecule. And now I have a carbocation. Let's put those CH3s back in again so we can see them a little more clearly. Okay, and now we're at the carbocation stage, so now we can rearrange. And remember, a carbocation rearrangement is where we look over to one side or another and we try and steal some electrons, steal a bond that would result in a more stable carbocation. So what this carbocation sees is if one of these methyl groups picked up and moved over to the next carbon over, we call that a methyl shift, a 1,2 methyl shift. So we now have one methyl up here and one methyl down here. Now where does that place our carbocation? This carbon now has 4 bonds. It had only 3 before, but this carbon just lost one of its bonds, so the carbocation is now down here. Now why is that rearrangement favorable? It's favorable because we've gone from a secondary carbocation to a tertiary carbocation, which is more stable. So we always want to be on the lookout for any mechanism involving a carbocation. We want to be on the lookout for rearrangements because if it can find a way to stabilize, it will. Okay, how do we get to our alkene? How do we do our last step here? We need to form the double bond, so now we need to deprotonate. Where is the proton that we want to go for? We want to deprotonate. Okay, it's not going to be at the carbon of the carbocation. It's going to be one of the adjacent carbons, one of the beta positions. Okay, why did we not deprotonate in this direction? Because that would give us a double bond that is less highly substituted. So if we go for this hydrogen, that's going to give us the double bond between the 2 methyl groups. It's going to give us a tetrasubstituted, which is the most stable we can have. Okay, so in this case, because it gave us the major product, we didn't have to make this decision. I just want to kind of keep that in mind. Like if you had to predict the product here, this is the product. This is why you would get the product you did. Okay, so we need to deprotonate. What can we use to deprotonate? A minus is the safest bet here. We just formed A minus in the first step. So you can also see that this is catalytic in acid. For every protonation step, there's a deprotonation step. So we grab that proton and use those electrons to form a double bond. So we protonate, lose water, and then in this case we rearranged, and then we lost, we deprotonated to form the double bond. Okay, one more example. Let's think about a transform. If I had an alcohol here, starting with an alcohol, and I want to go to an alkene, it's important to consider the functional groups in our starting material and our product to decide how we're going to convert one to the other. Okay, we're back to our original problem. We want to form an alkene. The way we form an alkene is by eliminating to form the double bond. So, our choices are E1, E2. Those are the only elimination mechanisms we know so far. Those are the only ways we know how to make alkenes so far. We'll learn about some others down the road. Okay, and we have an alcohol. So what if we took this and we treated it with H2SO4 heat? We just learned that alcohols can be dehydrated, so certainly this alcohol could be dehydrated. Would that give this product that's shown as the major product? Now let's think about that mechanism. We know this is going to be an E1 mechanism. It's carbocation conditions. And so we're talking about a primary carbocation, highly unstable, but with immediate rearrangement we can get to a secondary carbocation, maybe even a tertiary carbocation. Okay, but most definitely we would rearrange this carbocation. What do you think that major product would look like if we had to predict this? I think we would end up forming the tri-substituted double bond, the internal double bond, as the major product. Okay, and because we don't want that as our target molecule, as the thing we're trying to synthesize, then this would not be a good synthesis. So what's another way that we can put in that double bond? We need to do an E2 elimination to form the double bond at the end here. So why don't we treat this with TB toxide? We talked about TB toxide as our bulky bait, throwing a little heat as our bulky base. What would happen if you took an alcohol and you reacted with T-butoxide? Would you expect the E2 elimination? What's wrong with trying to do an E2 here? You lose a beta hydrogen and what? A leaving group. We do not have a leaving group here with hydroxide. So this is no reaction because there's no leaving group. So if we wanted to try and do the E2, but that's not going to happen here. So how can we possibly do the E2 elimination? What do we have to do? We have to make the OH a good leaving group, and then we can do the E2. So an ideal way to do that is to to convert the alcohol to a tosylate. So we can use some tosyl chloride and pyridine. That keeps the alcohol right where it is, but turns the OH into an OTS, which is now a great leaving group. And now that you have this great leaving group, now you can treat it with T-butoxide and heat and do the E2 elimination. Okay, if you don't want to do the tosylate, you can maybe use something like thionyl chloride, SOCl2, or PBr3 to convert it to a bromide or a chloride. Okay, then we have a good leaving group and we can do an E2 elimination. So we want to keep in mind in synthesizing alkenes, we want to think about, we need to know the mechanisms very well for the E1 and the E2 and decide which is appropriate in each condition, in each situation. Okay, next we'll be talking about the reactions that we can do for alkenes once we have a carbon-carbon double bond in our structure.